All right, section 4.2, we're going to start with a word that I used in the last lesson just a moment ago, the word prime. And we're going to be talking about prime numbers and composite numbers. So prime numbers are any positive integers with exactly two distinct positive divisors. Please write down yourself a note that says 1 is not prime. 1 does not have two distinct factors. It only has one factor, 1. So let's list a few of our distinct primes that we know, and I will start us off with the numbers 2 and 3. So what's the next factor, the next number after 3 that is prime? 5. And then what? 7. So 9 doesn't work. It's really tempting to just go by, every odds, but 9 doesn't work. Why? Yeah, because it's also divisible by 3. So we have to skip 9, and we would go to 11, and it is prime. So it is important to realize that except for the number 2, no other even numbers are going to work, because all the even numbers after 2 are also divisible by 2. So I can just sort of skip through my odds to look for them, and some of them work and some of them don't. So there's infinitely many primes. Every now and then in the math world, somebody on their grad school project would find the new biggest prime number known to man kind of thing. So there isn't a biggest, right? There's always something that can be found bigger, but it becomes more and more difficult the farther you go. Composite numbers, on the other hand, are positive integers with more than two distinct positive divisors. Again, 1 is not in this list. 1 is not prime, and it is not composite. It is something else. It's other. Okay, so this is not something that's just one or the other. There are things that don't fit in either category. 0 would not fit in either category as well. But there's plenty of numbers that are composite. So again, you're going to mostly be picking things. You can definitely pick evens, right? That's going to work except for the number 2. So we could start with 4, and then we could go to 6, and then we could go to 8, and then we actually get 9 on this list, right? And we get 10. And again, there's infinitely many composite numbers as well. We call something a factorization if it is any expression of a number in factored form. So it doesn't have to be completely factored to be a factorization. It just has to break it down somehow. And dividing something by 1 is not considered breaking it down, so that's not acceptable. But for example, we could take something like the number 12, and we could break it down into 4 times 3. This isn't primes. It's not broken down as far as it can be broken down, but it is partially anyway factored, so this is a factorization. But then the ones that we use more frequently are the prime factorizations, where we take all of the pieces and we break them into their prime components. So we can use the same 12 that I had before. And if we were to break the 4 down into 2 times 2, and we still had the 3, all of that also would equal 12. And all of the factors on the right-hand side, 2, 2, and 3, are all prime. Prime factorization, we'll see in a moment, is unique. That's actually the reason that people tend toward it as opposed to factorization. Factorization may have more than one form for a particular number, but prime factorization has one and only one form, except for the potential ordering of the numbers. We'll have that definition later, or that theorem later. What we're going to do right now, though, is we're going to actually see 3 different uniquely designed problems and how to find their prime factorization, and then we will pause for the day at that point. All right, so the first one is sort of the traditional one that children encounter first. Maybe it's a little bigger than they encounter, but It is the type of number. It's just a number with all its digits. It's all written out in sort of like simplified looking form. So I'm going to show you two different ways to do prime factorization. I suspect that there are others, but these are two common ways. You may have seen them both. How many of you have seen factor trees? Factor trees is what I grew up with. That was what we were being taught the whole time. And there's good and there's maybe not so good stuff about factor trees. One of the good things is that they're very flexible. You can choose as your first factoring step anything that divides this. So if you look at it and you're like, I have no idea, but it's even, it'll divide by 2, you can start with dividing by 2. On this one, you probably look at it and you at least see the 0 at the end, which means it's divisible by 10. And you could do 5 if you wanted to as well, but 10 works, so I'm going to go with 10. Nothing special about it except that it's a little bit bigger than the number 2, so that I break my numbers into smaller components when I can look at both of them. And I keep going until I have primes at the end. So 10 breaks into 2 and 5. Again, 2366, you may look at that and go, I don't know, it's even. That might be the best you can do, and if so, then you just do that. And you say, okay, it divides by 2. But then you need to know, what is 2366 divided by 2? Your calculators are perfectly fine to use. What would 2366 divided by 2 be? It starts with a 1. Channing's going to get it for us. What'd you get?
1,183.
Yes, ma'am. 1,183. Now, it's possible 1,183 is prime. I mean, like, right, that may not be a number that you know off the top of your head whether it's divisible or not. And so if you're not sure, we should just start with the lowest primes and work our way up trying to work through them. It's clearly not even, so we don't need to try to divide by 2. Does it divide by 3? I mean, I know we have a calculator we can just plug it in and check on, but from the rules, you haven't done any homework on it yet, but from the rules, is this divisible by 3, 1183? No, why not?
Because it doesn't add up to a number.
Right, so 1 plus 1 plus the 8 is 10 plus 3 is 13. 13 is not divisible by 3, so this won't be either. We also know it's not divisible by 5 because it doesn't end in 0 or 5. That's my next prime number. So 7 would be next, and I don't have any rules for that. So if you try to divide 1183 by 7, will it work? Check for me.
Yes.
It does. What does it give you as the result when you do the division?
169.
169, and you might be familiar with 169. Oftentimes people are. Do you know what 169 is? Yeah, you're right, Rylan. It's 13 squared. And if you weren't sure, we just keep working our way up. We don't have to go back down to checking 3 and checking 5. We don't have to do that. We just continue to start with 7. We'd say, okay, 169 to divide by 7. You'll find out that it doesn't. Okay, what's my next prime after 7? It's 11. We try to divide it by 11. It won't work. And then we get to 13, and it would. So the flexibility within the trees are very nice. The catch to the trees is that if you tend to be a little messier in your handwriting and so forth, you very likely might lose something at the end of one of your branches that you needed. So be careful if you choose to use this method and capture all of the ending branches that had all of your prime numbers. So these are all of mine. 2, 5, 2, 7, 13, 13. And the way that we generally see this written is we take the base. We'll start with the smallest one, a 2. And we ask ourselves, how many 2's are there? There's 2 of them. So we write this as 2 squared. So there's one of the 2's and the other 2. What's the next smallest value? 5. I'm going to use dots because at this point we might encounter x's at somewhere, so I'm just going to use dots between things. A times a 5. 5, there's only one of them, so that's all I need. What's my next number? 7. There's only one of those. And then I have my 13, and there are 2. How could you check to make sure that this is a prime factorization for the original number 23,660? You can multiply back out. You absolutely could. Or your calculator could if you prefer. Yeah, so you should visually check to make sure you've got primes as all your bases, which we do. And then you could actually multiply it all back out to make sure it gives you 23,660. Okay, so this is one way. The other way, I'm kind of a fan of the other way personally, because it puts a little more structure in place, which means that I have to worry less at the end about collecting all my pieces, is to do a division bracketing. So we're going to do the 23,660. And what we do is we divide by the smallest prime number it divides by. So in this one, we are hemmed in. We don't have the flexibility to decide, oh, look, it divides by 10. No, we divide it by the smallest prime number, which would be 2. So grab your calculator, take 23,660 divided by 2, and tell me what you get. It's going to go, the division's going to go downwards on this instead of going upward, kind of like we would have done on the other ones.
11,830.
Fabulous. And at that point, it's still even, so we would divide by 2 again. So 11,830 divided by 2, what do we get?
5,915.
Okay. So at this point, it's no longer divisible by 2. I know you probably look at it and go, well, it's 5 next. You still have to pass through 3 and make sure it doesn't work. So you need to visually, or at least check that the 3 doesn't work. So 5 plus 9 is 14, plus 1 is 15, plus 5 is 20. So it won't work. So then we move on to 5s. 5915 divided by 5, what does that give me?
1,183.
Yeah, which should look familiar. We've already seen that today in the previous method for this particular problem. So we happen to know now that it divides by 7, leaving me with 169, which is the 13 and the 13. And I like this because all of the values are right there in a row, and they're in order, which is also friendly. So I have 2 squared times 5 times 7 times 13 squared. There's nothing special in your book that says which of these you need to use or have to use, so you can choose whichever one you like. It's not going to matter to me. But do realize that if you've got children in your class who are struggling with one, that there are other things that they could try that might be better for them. And so be aware that there's more than one option. All right, the other two are a little bit more unique. Like this is very commonplace. You see a whole number, you break it down into its pieces. This is pretty standard. These are a little bit different, the next two. The next one is sort of partially factored already, because I've got bases with exponents. But like I mentioned over here at the end, you should check and make sure that all the bases are prime. These aren't. 16, 81, and 6, none of them are prime. So we do not, let me repeat, we do not want to multiply this all back out. It is super counterproductive. It is already partially factored for you. So that's a blessing. Don't go taking it and making it a curse, okay? So what we need to do instead is we need to take each of the pieces that are not primes yet and make them in their prime form as well. So I'll do trees on these. 16 breaks down how? 4 and 4. And how do my 4s break down? 2 and 2. So this 16 right here is actually 2 to the 4th. Let's do 81 with the division pieces. What's the smallest prime number that divides 81? 3. 9's not prime. It does divide it, but it's not prime. If you're using trees, you can use your 9. This one, if I'm using this one, would be a 3. And if it divides, you're going to get a 27. What's the prime number, smallest prime that will divide 27? 3. Giving me a 9, which divides again by 3, giving me a 3. So this one, either way you do it, is 3 to the 4th. And we'll do a tree on the last one as well. 6. How does 6 break down? 2 and 3. So this one doesn't have any powers. It's just 2 times 3. So what does this mean we do? Well, it means I replace the 16 with 2 to the 4th. But what power was the 16 raised to begin with? A 4. So this is 2 to the 4th to the 4th. My 81 was 3 to the 4th, but it was also raised to the power of 4. And then my 6 is 2 times 3, and that's being raised to the power of 6. So this is actually asking us to utilize stuff we did back in chapter 3 with rules of exponents. When I have an exponent raised to an exponent, what do I do to consolidate or combine those? We multiply. So this is 2 to the 16th. Same thing happens on the 3, so it's 3 to the 16th. The one over here has 2 numbers multiplied raised to a power. What does the process, what process can we do to consolidate or simplify that? Do you remember what property applies? What's that? Yeah. The 6 can apply to each of the terms individually. It can be distributed. So this is 2 to the 6th and 3 to the 6th. But prime factorization consolidates all the bases that are the same into a single base. So I have 2 to the 16th and I have 2 to the 6th. What do I have to do to write them as a single 2 to a power? Yeah, add their exponents. What is 16 plus 6? 21, 22, I think, yeah, 22, yeah. And I happen to have the same exponents on the other one. I mean, I wouldn't have to, but they are on this one. 3 to the 16th and 3 to the 6th, so this is also a 3 to the 22nd. Okay, are we good? Okay. One more, and we will pause for today. The last one, again, kind of like the previous one, looks like it's in partially factored form. And in some ways, it's even better because they're all prime factors on the bottom, right? They are. But there's addition. There's no addition in factorization. It's all multiplication. But again, I don't want to distribute and multiply this all back out. That would be horrid. That's a power of 55. It is not going to be good, and your calculator is not going to give you good numbers back at you. It's going to turn things into scientific notation. So what do we do? Well, we recognize what pieces they have in common. In particular, they all have the same sets of bases, right? They do. They have a 2, and they have a 3, and they have a 7. How many 2s do they have in common? 2. One of them has 2 2s, the other one has 4 2s, so the ones they have in common are 2. Total between them 4, in common 2. Okay? How about the 3s? How many do they have in common? 4. 5 in the first one, 4 in the second. And how about the 7s? 55. That's the easy one because they match perfectly. So what we're really doing here is we're factoring out what they have in common. And what always goes next is the same structure it started with. This is 2 numbers being added, so I'm going to have 2 numbers being added in the parentheses afterwards. Okay, if you've lost something along the way so that there's no addition, you've lost something. You need to go back and find out what it was you lost. So what we want to do is piece by piece go through and figure out if we've got everything. So the first one, 2 squared, I took out a 2 squared. So there's no more 2s. I took them both out. The second one has a 3 to the 5th, and I took out a 3 to the 4th. So there is a 3 that is still there. And then the 7 to the 55th, all pulled out, right? So if I were to multiply this by this, I'd end up back with this at the top. Okay? We're going to do the same thing with our second piece. So looking at the 2 to the 4th, and I took out 2 squared, what's left? 2 2 squared. Looking at 3 to the 4th, and I took out 3 to the 4th. What's left? Nothing. I mean, like 1, right? But no additional values that I need to put in there. And then the 7 to the 55th. Nothing additional on that piece either, right? So again, I'm not supposed to have any addition, so next I need to do is to simplify this. This is 3 plus what? 4. 2 squared is 4. And what's 3 plus 4? 7. So the piece that I have at the beginning can simply be rewritten again. And again. And now it's times 7. But now I have duplicate bases one more time. That doesn't always happen when we get to this point, but it did on this one. So 7 to the 55th and 7 to the 1st make what? How many? It's already 7 to the 55th, so 7 to the 55th times 7 to the 1st. Do you remember what you do with the exponents? You add them. Yeah, so we need to add the 55 and the 1 to make it 56. Powers raised to powers multiply, powers multiplied by powers add. Now it's just as likely at the end that I didn't end up getting 3 plus 4 is 7, I got 11. Okay, fine, it'd just be times 11, right? It's also likely when I get to this point that I factor something out completely, like when I asked you how many 2s are left or how many 3s are left and you said there aren't any left. But remember, you're dividing things out, so there's always the number 1 left. So in some sense, although we didn't write them, it's kind of like we had 2 squared times 1 here. So in between the addition, there's going to be a 1 plus something else if you've taken everything out. It's not a 0. It's division, it takes things out, you're left with the number 1. All right, we'll stop there.